in this question you can see that there is a uniform ladder of total length 5 meter and it is placed against a wall and a floor. So the coefficient of friction of wall and floor is given as mu, and we have to find out the minimum value of mu so that this ladder would not slip. So let us first of all draw all the forces which are acting on this ladder. So this is the normal reaction of the ground and this is the normal reaction of the wall. So let us name them as N1 and N2. So this is N1 and this is N2. And the friction acting on the rod due to wall would be in upward direction. So it is F1, and the friction acting on the rod due to this floor would be towards this side, towards right hand side. So this is F2. And the mg acting on the rod would be in the downward direction, acting from the center. Okay, so now the value of friction F1 would be mu into n. In fact, let us name this as F2 and this as F1. So F1 would be equal to mu into N1 and F2 would be equal to mu into N2. So this is first equation, this is second equation. Now we know that the net force acting on the rod is 0 in x-axis as well as in y-axis. So let us first of all equate the forces of x-axis, and therefore you can see that friction F1 is equal to N2, and obviously we know that friction F1 is mu N1, so mu N1 is equal to N2. This is the third equation. And similarly Fy is equal to 0, therefore N1 plus F2 is equal to mg. So this F2 is equal to mu N2, so N1 plus mu N2 is equal to mg. So we can substitute the value of N1 as N2 by mu. So this is N2 by mu plus mu N2 is equal to mg, and therefore this is N2 1 plus mu square is equal to mu mg, and N2 is equal to mu mg by 1 plus mu square, and N1 would be N2 by mu, so N1 would be equal to mg by 1 plus mu square. So these are the values of N1 and N2 in terms of mu. Now let us equate the torque. So let us equate the torque about any of the point. So let us choose this point A and let us equate the torque about A. So we know that the torque about A would be 0 because rod is neither rotating nor it is sliding. So the torque of forces N1 and F1 would be 0 because they are itself passing through point A, and therefore their torque would be 0. And the torque of F2 would be this F2 into perpendicular distance, and this distance would be 3. So torque of F2 would be F2 into 3. So this is F2 into 3. You can also see that F2 would rotate this rod about point A in anti-clockwise sense, like that. Okay, and again the torque of N2 would be N2 into this distance. Now this distance is 4 meter, so the torque of N2 would be N2 into 4, and a positive sign is appearing with N2 because the sense of rotation of N2 is also in anti-clockwise sense. So the torque of N2 and torque of F2 are supporting each other. Now the torque of mg is in clockwise sense, so there would be a negative sign, and torque of mg would be mg into this distance. Now this distance would be 1.5. So torque of mg would be minus mg into 1.5. That is equal to 0. Now we know that F2 is already mu n2 into 3 plus 4n2 is equal to 3 by 2 of mg. Now we know that this is n2 into 3 mu plus 4 is equal to 3 by 2 of mg, and the value of n2 is equal to mu mg upon 1 plus mu square. So this is mu mg upon 1 plus mu square into 3 mu plus 4, and that is equal to 3 by 2 mg. Now cancelling this mg with mg, the equation which we have got is 6 mu square plus 8 mu is equal to 3 plus 3 mu square. So this is 3 mu square plus 8 mu minus 3 is equal to 0, and I'm again writing it as 3 mu square plus 8 mu minus 3 is equal to 0, and you can see that this is 3 mu square plus 9 mu minus 3 is equal to 0. So this is 3 mu is common, and this is mu plus 3 minus is common, and this is mu plus 3, and that is equal to 0. So the roots are mu plus 3 and 3 mu minus 1. So we know that this root is not possible because mu cannot be negative. So this is the correct one. So mu would be equal to 1 by 3. So the correct answer would be option number C. Now let's move on the next question. In this question, you can see that there is a rod which is kept by leaning on the wall and the floor, and the wall and floor are frictionless. It is given in the question. Now to keep this rod in equilibrium, we have to apply some force P at the lowermost end of the rod, and we have to assume that the mass of the rod is m, and we have to find out the minimum value of this applied force P so that rod remains in equilibrium. Now let us first of all draw all the forces acting on the rod. So the mg of the rod would be acting from the center in the downward direction. The normal reaction of the wall would be acting in this direction. So let us name it as N1, and the normal reaction of the floor would be acting in this direction. So let us name it as N2. So these are the forces, and as well as P is also acting in this direction. So these are the forces which are acting on the rod, and we know that due to application of this force P, the rod is in equilibrium. Rod is neither accelerating and neither rod is rotating about any point. So we can say that the force acting on the rod in x direction would be 0. Therefore, N1 would be balancing out P. So this is the first equation. And we can also say that the force acting on this rod in y direction would be also 0. So N2 would be balancing mg. Okay, now this is the second equation. Now the third equation can be obtained by writing the equation of the torque. So we can write the equation of the torque about any point, because neither of the point the rod is rotating. So we can balance the torque about any point. So let us balance the torque about point A. So this would be the torque of rod about A would be 0, and the torque of mg, in fact torque of N1 would be 0, because N1 is passing itself from point A, plus the torque of mg would be mg into this distance. So we can find out this distance by this angle is theta, and if the length of the rod is L, then this would be L cos theta, L by 2 cos theta. So this would be mg into L by 2 cos theta. You can also see that this mg is rotating the rod about point A in clockwise sense, and n2 is rotating the rod about point A in anti-clockwise sense. So we can write the torque of n2 and the distance of perpendicular distance of n2 from point A is L cos theta. So this would be in anti-clockwise sense, so minus n2 into L cos theta. Okay, and the torque of P would be in clockwise sense, so it would be plus P into the distance of P from A, perpendicular distance, would be L sin theta. So P into L sin theta would be equal to 0. Now you can see that n2 is already equal to mg, and therefore this equation would be minus mg L by 2 cos theta plus P is equal to n1, so we have to find out P only. So plus P L sin theta is equal to 0. So cancelling this L with L, P would be equal to mg cot theta by 2. So this is the force required to keep this rod in equilibrium, leaning on wall and floor. Now let's move on the next question. In this question, you can see that there is a rod of 1 meter length and it is kept by a wall and floor supporting it, and the floor and the wall are frictionless, as well as we are holding the rod in this position, and now as soon as we release this rod from this position, we have to find out the angular acceleration of this rod. So to solve this question, let us use the method of instantaneous axis of rotation. So we know that the velocity of this end of the rod, while it would be slipping, would be in downward direction, and the velocity of this end would be in forward direction. So this is VW and this is VH. So if we have to find out the instantaneous axis of rotation, so we can see that if we draw the perpendicular to the velocities, then the point at which any two perpendicular are intersecting with each other is IAR. So this is the IAR of the rod. Now we can see that the mg of the rod would be acting from the center in the downward direction. So this is the mg of the rod, which is acting from the center in the downward direction. This is mg, and this distance is 1 by 2 cos 53. So let us assume it as x, and this distance is 1 by 2 sin 53. So let us also assume that this distance from the center of the rod to IAR is r, and therefore if we find out the moment of inertia of the rod about IAR, so we have to apply parallel axis theorem. So this would be ICOM plus m r square. Now ICOM of the rod about its center of mass would be m L square by 12, where L is equal to 1. So this is m by 12, and the value of r is under root of 1 by 2 sin 53 is 4 by 5 whole square, plus this is 1 by 2 cos 53 is 3 by 5 whole square. So the value of r would be under root of, this is 4 by 25, and this is 9 by 100. Okay, so the value of r would be, this would be under root of this is 16 plus 9, which is 25 by 100, which is 1 by 4. So the value of R would be 1 by 2. So the moment of inertia of this rod about IAR would be ICOM, which is m by 12, plus mr square, which is m by 4, because we are using r square. So I about IAR is equal to m by 3. Now we know that in this case the rod is slipping and we have to find out the angular acceleration. And we also know the significance of IAR, instantaneous axis of rotation. And it is the fact that all the motion of any body which is in the state of translational and rotational motion, so we can assume all the motion of that body about IAR to be perfectly rotational motion only. So if we are assuming the rod to be performing only rotational motion about IAR, so we can just find out the torque acting on the rod about IAR. So the torque acting on the rod about IAR would be only due to mg of the rod, and it would be mg into perpendicular distance. So this would be the distance of line of action of mg from IAR, and this distance would be 1 by 2 cos 53. So it is 3 by 10. So this is the torque of rod about IAR. And also I'll tell you that there would be two other forces. This is the normal reaction of the wall and this is the normal reaction of the floor. So these forces are passing through the axis of rotation. Therefore, the contribution of these forces in the total torque would be 0. So the total torque about IAR would be equal to I about IAR into alpha. So if we substitute the values in this equation, so I can write that this is 3 by 10 and mg is 10. It is equal to IAR m by 3 into alpha. Cancelling m with m, 10 with 10. Alpha is equal to 9 radians per second square. So this is the required angular acceleration of the rod. And mind you that this angular acceleration alpha about IAR would be same as that about the center of mass of the rod. So the answer would be 9. Now let's move on the next question. In this question, you can see that there is a uniform rod of length L and mass 1.6 kilogram. It is kept at rest on a wall, and it is hanging on the wall in such a way such that some of its part is lying above the wall. The floor is rough and the angle the rod makes with the wall is 30 degree. So we have to find out the ratio of H by L and friction F which is acting on the bottom of the rod if this normal reaction exerted by the floor and the wall on the rod are equal. So let us first of all draw the components of normal reaction. This angle is 60, so this would be n cos 60. Now n cos 60 is obviously n by 2, so let us write it only as n cos 60, and this component is n sin 60. We know that this rod is in equilibrium, therefore the x component of the net force acting on the rod is 0. Therefore we can say that the friction acting on the rod will be equal to n sin 60. Now friction is n sin 60 is root 3 by 2. This is the equation number 1. Now equating the forces of y-axis to be 0, so we can say that n cos 60 plus n, this is n cos 60 and this is n, and these two are equal to mg. So these are equal to mg. So this is 3n by 2 is equal to mg, and mg is 16. So n will be equal to 32 by 3 newtons. This is 16 newtons. So this is the value of n, and the friction will be equal to, this is 32 by 3 into root 3 by 2. So it is equal to 16 by root 3. Okay, now let us balance the torque. So we'll balance the torque about point A, because in that case the torque of friction and normal reaction would become 0 and the equation would be shorter. So balancing the torque about A to be 0, we can say that torque of mg would be mg into this distance. Now this distance is, let's suppose, x, and let us first of all find out the complete distance, this one. We already know that this is L by 2 because the complete length of this rod is L, and obviously this is L by 2 because this is the center of mass of the rod, and this angle is 60 degree. So this x would be equal to L by 2 cos 60. You can find out the component of L by 2. The component of L by 2 along horizontal is L by 2 cos 60. So x is equal to L by 2 cos 60, which is L by 4. So the torque of mg is mg into L by 4, and the sense of rotation of this torque about A is clockwise. Now the other force which is producing some torque about point A is this normal reaction, and this normal reaction is at some distance, this. So this distance can be calculated. Let's suppose this is y, this complete distance is y. So we can say that cos 30 is equal to h upon y. Cos 30 is equal to h upon y, and therefore y is equal to 2h upon root 3. So the torque of this normal reaction will be n into this distance y, because this normal reaction is itself perpendicular to the rod, and therefore the perpendicular distance of this normal reaction from the point A would be y. So this is n into y is the torque of normal reaction, and this torque is in anti-clockwise sense. So there would be a negative sign with the torque of n. So this would be minus n into y. So that is equal to 0. So mg into L by 4 is equal to n into y. So mg is 16, L by 4, and n we have already calculated that n is 32 by 3. So this is 32 by 3, and y is 2h by root 3. So you can see that this is 4 and this is 8. So L by h is equal to 16 by 3 root 3. So I guess we have to find out h by L. Yeah. So h by L will be equal to 3 root 3 by 16, and therefore the friction would be 16 upon root 3. So the correct option would be option number D. Now let's move on the next question.